the quantum teleportation, okay? Now, this is very interesting. What we are doing is this. We're going to transport information of a qubit from one location to another location instantaneously. So this is cool, right? But just information. But think about electron are identical. If I transfer the property of my electron to the electron I'm going to teleport to in the Mars, isn't that it's just like I teleported this electron to that electron at no time? I even think, I don't know if that works, I teleport the wave function of all the molecules in my body to all the corresponding molecule in Mars. Isn't that I will be there instantaneously, just like teleportation? Right? You can think about this. I don't know, right? But the point is, you definitely, based on what we just learned, there's no cooling theorem. When I teleport myself to Mars, I must destroy myself at the same time. Otherwise, I have two copies in the universe, exact copy. So quantum teleportation is that I teleport my information of one atom to another place, then the information will lose at my place. But that is very dangerous, right? You might say Einstein is going to be very unhappy because you can transfer information in no time. To have teleportation successful, unfortunately, you need to call the person on Mars 2 times through classical channel so that they will do the appropriate operation to repeat what you have. Okay? So that's no problem. This is a little bit old, but I think last time, maybe 2 years ago, a group in China was able to do this satellite quantum teleportation through about 870 miles. Okay? Electrons, I think they use photon probably. Photon stays here and then teleports to 870 miles away. I don't know, to Vancouver or something from here. Yeah.
So this has nothing to do with
you need entanglement. You need entanglement to do this. Yeah. Let's take a look, right? I give you an overview first. Very sophisticated algorithm. This is a fake one, actually. It won't work. I will tell you why. And then we'll look at the working version. Alex and Bob, right? Bob has a state which is 0 on his qubit. And Alex has a state, alpha plus beta, which she doesn't know what it is neither. She doesn't know. She has no idea. Okay? They will do a control NOT gate. So in this control NOT gate, you then form an entanglement of these 2 qubits. I will explain more. I just give you the overall architecture. This is where this algorithm doesn't work. If I'm on Earth, Alex is on Earth, and Bob is on Mars. How can you make a control NOT gate that is doing the controller of 2 qubits separate so far away? I just told you that a control NOT gate even cannot do this 2 qubit that is only maybe 10 micron apart or 100 micrometer apart, right? That's why this won't work. But we will have a solution to fix this. But let's look at this first. We get this one. You see that after this control NOT operation, I have a superposition state, and somehow the Bob state is in the superposition of alpha 0 plus beta 1 and alpha 0 minus beta 1. Okay? And the strategy is this. Alex is going to do a measurement in the plus minus basis. If she get plus, she's going to call Bob. Hey, I got plus. Then Bob knows that because the wave function is going to collapse to this one, right? Because this is a superposition. Then Bob said, fine, I already got your state because my state is alpha 1 plus beta 1, which is the same as Alex's original one. But Alex can also get minus during the measurement. Once it get minus, then the whole wave function collapses to this one. And then the state on Bob's system is alpha minus beta. which is not the original one. But Bob knows that it is alphas minus beta because Alex called him, say that it is minus, that what she got. He only need to apply a Z gate to rotate it so that it becomes plus. Through this process, the Bob will acquire the state of Alex. Okay? I know, very confusing, but we will go to the math and then it will be very clear what's going on. Any questions? Maybe no, right? Because too confusing. Yeah. Say again? It is not. Because what is the state of Alex? It becomes plus or minus, right? It is not zero. So it is not a swap gate. Yeah. And definitely swap gate is reversible. This involved measurement is not reversible. Yeah, very good question. Okay, so let's redraw the circuit. I'm going to draw it in this way. I have Alex. See, here I confuse you again. This time I put Alex on the top, which is the MSB. It's going to be different from what I drew here because now the bottom is MSB, the top is LSB, but now I put the bottom LSB, top MSB. This is the circuit you will get in IBM-Q, right? I have example in my book that is the IBM-Q1, MSB is at the bottom, right? But it doesn't matter, it won't stop us. So what do we do? Yeah, we say that we do have a control NOT gate here. The Alex start with psi equals to alpha 0 plus beta 1. Okay, and Bob is at 0. So what is the total wave function in this case? The total state. How do you write it? In this state, it is alpha 0 plus beta 1 tensor product 0, right? Because Bob is the LSB, okay? Which is equals to alpha 0 plus beta 1 0. Is this okay? But now we go through the control NOT gate. What would it be after the control NOT gate? Now you can use matrix, but now you're good enough. You know that every operation is linear and also if obey the distribution law. So alpha 0 will become what? Still 0 because the controlling qubit is 0. How about beta 1 0? It will become what? 1 1, right? Because the controlling qubit is 1. Okay, feel free to leave now if you want to leave. I will just continue the next half hours. Okay, it becomes beta 1 1. This is entanglement. That's what you ask. We do use the entanglement to play with this. Okay, that is the first thing. Entangle. Okay, so this is step 1. And then I call this step 2. Now, Alex is going to measure in the plus minus basis. Okay, what will you get? In order to know that, I want to do some transformation. Alpha 0 plus beta 1 1 is actually have 0 plus beta 1 1, right? And recall that what is 0? 1 over square root 2 plus minus. Okay? I do this just because I want to do the math easier. This is what is 1 in the plus minus basis. Plus minus, right? If you forgot, you can go back to learn this, right? It's just like plus is 0 plus 1, minus is 0 minus 1, right? So let me shuffle the terms. First of all, because I'm talking about measurement in plus minus basis, so naturally I'm going to factorize plus. And for this plus, what do I have? I have alpha 0 and beta 1, right? So this is alpha 0 plus beta 1. For the minus term, I have alpha 0 minus beta 1. Do you see that? Because this minus term has alpha 0 and this minus term have negative beta 1, right? So that is exactly the equation I showed you earlier. Now, if I do a measurement, right, it can collapse to plus, right? Once it collapses to plus, the whole wave function will collapse to alpha 0 plus beta 1, right? Because this is a superposition of two wave function. And Bob has this, okay? And that is the state that Bob has, right? If it collapses to minus, then it becomes minus alpha 0 minus beta 1. And Bob has alpha 0 minus beta 1. Make sense? Make sense?
One more time.
Look at this superposition. The whole state of the whole system is plus this thing plus minus this thing, right? This one you are okay, right? No, there's not related to diagram. It is here already. This diagram is only nice now. It doesn't have anything related to this one. This is just a reorganization or rewritten this one to this form. This one is exactly the same as this one. I write in this one because I'm going to measure in plus minus basis. So now if I get plus, then this one will be the one that Bob has. If I get minus, Bob has this one. That's all I'm trying to do. Because once you collapse, because this is a superposition of this whole term, right? This is one qubit, this is another qubit. This is one of the states of the system. This is another state of the system. And this is a linear combination, a superposition. So once I do measurement, you need to collapse to either plus or minus. Yeah. No, LSB. No, this is MSB plus, right? The plus is Alex, and then the rest will be Bob's. Yeah. So that's why Bob becomes alpha 0 plus beta 1. The relation? Yeah, because I have two qubit, right? This is the first qubit. The last qubit is Bob's. It's a linear superposition. It's a superposition, right? So if I get plus, Bob will get this one. If I get minus, Bob will get this one. And all I need to do is call Bob. I say I got plus. Then Bob just apply identity gate, do nothing. It has the state already, right? Bob already have this state, doesn't have to do anything. But if I get minus, I call Bob, then Bob will apply a Z gate. Z gate is what? 1, 0, 0, negative 1. Right? Then it will convert this one to alpha 0 minus beta 1 becomes, after apply Z gate, alpha 0 plus beta 1 by definition. Okay. Okay. Let me move to another rule from, right? Last time we talked about quantum teleportation. Let's review what we did again. We have two persons, Bob and Alex. Here I put Alex as the MSB, most significant bit, and I put it at the bottom, right? So when we write it, Alex will go first because it's the MSB, right? Now, Bob and Alex are in different lab. Maybe Alex is in San Jose State U, Bob is in UC Berkeley, very far away. Alex has a qubit with some information, even she doesn't know. That's the main point. She doesn't know what is the state of that qubit. So it can be, in general, alpha 0 plus beta 1. Bob has a qubit initialized to 0. Okay? They are going to do some entanglement by using this gate. What is this gate? Control NOT gate. Very good. The control NOT gate, now you might find there's a problem because I need to have one control NOT gate controlling two qubits 60 miles away. One is San Jose State, one in UC Berkeley, right? So then what will we do? Let's say we can make this control NOT gate. This control NOT gate, which one is the controlling qubit? The MSB, the Alex, right? This is the controlling. Because we have this controlling qubit, we can use matrix, but now we are very good already. We kind of understand the meaning of the basis, right? So when I do this, when in the first state before the control NOT, the total wave function, right, or the total state is psi A, 0B equals to alpha 0, 0 plus beta 1, 0. Correct? Because Bob is 0, right? So this is 0, 0 and 1, 0. Is this okay? You just combine them, right? And what is the meaning control gate? We know, again, very fundamental. You must memorize. The definition of any gate is on how it transforms the basis vector. And Schrödinger equation is linear. Quantum mechanics is linear. I can do it by each basis one by one and then add them together. So how does a control NOT gate transform 0, 0? Controlling bit is 0. That's why I do nothing. That's why after control NOT gate, I still have alpha 0, 0. How about 1, 0? Controlling qubit is 1. Then it's going to negate the target qubit. That's why after the control NOT gate, it becomes 1, 1. You see that when you are very familiar with this, you will be able to write this and even derive equation, come up with your new algorithm, right? You don't need to go back to the matrix. So remember, the definition of the gate is how it transforms the basis vector. And because quantum mechanics is linear, you can treat them one by one and then combine them together. Okay, so you know that you are doing the right thing. With this, then we try to expand this into this combination. Why? Just the genius, they came up with this idea, right? They can see that. So they found that if I represent the Alex basis in plus minus basis, Alex qubit in plus minus basis, Bob's qubit will acquire the form of Alex's original qubit. This one is just equal to 1 over square root 2 plus alpha 0 plus beta 1 plus 1 over square root 2 minus alpha 0 minus beta 1. You can just extend it. You know what is plus, right? You know plus equals to 1 over square root 0 plus 1, right? And minus equals to 1 over square root 2, 0 minus 1. We have done this many times. Just do the substitution. You find that they are the same. Now, why do we want to do this? Because now, if Alex measures this in plus minus basis, then the wave function will collapse to either the first term or second term. Is that okay? Yeah, because the first term is 2 qubit, second term is also 2 qubit, right? The second qubit is in a superposition state of alpha 0 plus beta 1. This here is superposition state of alpha 0 minus beta 1. So if I measure get plus, Alex will give a call, right? I will call Berkeley, say, okay, I got plus. I don't know then, but based on theory, Bob knows that he has alpha 0 plus beta 1 already. So he already has the state of Alex qubit. Then he basically does nothing, or you can say apply an identity gate. Quantum teleportation is successful. What if Alex got minus? Give a call to Bob, say, oh, unfortunately, this time I got minus. But Bob knows that what he has is alpha 0 minus beta 1. Very close, but not exact. What can you do? Apply a phase shift gate, C. What is C? C is 1, 0, 0, negative 1. And Z, if you remember how you even don't need the matrix, right? If you remember how it does, for 0 basis state, it does nothing. For 1 basis state, it applies a 180-degree phase shift, negative 1 to it, right? And that's why this becomes plus beta 1. So by doing C, he did not do any measurement. He still don't know what state he has. But he knows that his electron state is the same as Alex's electron state. So we successfully done the quantum teleportation. Yeah.
So that's the thing.
That is the main thing, right? The electron state in this lab now is in Berkeley now. Does this violate no cloning theorem? Very good. It does not. Because in order to have this complete, I need to do measurement on the first qubit. It collapses to either plus or minus. Definitely it's not alpha 0 plus beta. Okay? So there's no cloning, no violation of cloning, no cloning theorem. Right? That's one thing. Why this is quantum teleportation? Why it's called teleportation? As I said, you are not really teleporting the matter. You did not make the electron to there, but you're transferring the information of the electron. But on the other hand, in my opinion, electrons are identical. If I have transferred the state of this electron to the other electron, effectively, it's the same as I teleport my electron to there, if I don't consider any relativity violation or energy transfer, right? Effectively, it is there right away. And I even think that if someone can prepare exactly the same particle on my body, if I can teleport all state to there, I will just live there. And here, the one, I will collapse because all my electrons just become plus minus states, or all my nucleus. It's no longer me, right? So I teleported there. Can this transfer the signal faster than the speed of light? You cannot, right? Once I measure, yes, suddenly Bob will get my state. But however, I need to call Bob first. In order to call him, I need to use classical channel, optical fiber or whatever, so that he knows what to apply to his qubit, right? So I'm not transferring information faster than the speed of light. Okay? Now, so what is the problem of this one? It is that we cannot do this control NOT easily, right? Because I need a very huge control NOT gate. So a more useful version will be this one, right? It's a little bit confusing, but the point is to let you appreciate all the math. The whole page, the purpose is to replace the C NOT gate. Okay, so let's see how we do it. I still have Alex as the MSB. Alex is here. And I have Bob as the LSB. Now I introduce something called auxiliary qubit or ancillary qubit. These qubits are very poor. They are critical. Your quantum algorithm won't work without them, but they are useless once they are used. They're just like the toilet paper. Once you use it, you don't care about that, but they are so important, right? So what do? We include this 0 BB. The first thing is that we want to do an entanglement with Bob's lab. So first, this qubit is with Bob in Berkeley. Okay, Bob has 2 qubits in his lab. Alex is in San Jose State U. This is in Berkeley. So he applied a Hadamard gate and then the control NOT gate so that he get an entanglement. Okay, so I won't go into math because in the next page I will show you the math, right? But the goal is that we want to entangle these 2 qubits. It's still in the same lab, easy, they can do it, right? Then you need to send this auxiliary qubit or ancillary qubit to San Jose State U, send to Alex. So this is another classical transport. Okay, you send it to me, but we do nothing. Actually, we are not doing any quantum teleportation. We just prepare for the future use. You entangle F for the qubit you have sent to me. I just keep it on my lab. We need to make sure the entanglement does not break, maybe through optical fiber or whatever. Yeah, you need to do that, right? So I keep it. I have this BB with me in Alex's lab. I have Alex stuff. Now suddenly, let's say Alex decided to teleport the state, which she doesn't know, to Bob. Then she will start working with this qubit. This qubit is now in Alex's lab, right? You see that, okay? She will do an entanglement again. So in this process, what will happen? It will going to form these states. We'll go to the math again. This is just an overview. After this entanglement with this C0 gates, we will get this complex structure, okay? And then Alex is going to measure the BB, not her qubit, BB, right? Because now we cannot damage the qubit yet. Going to measure the BB, the one that Bob sent me, okay? Remember, we have 3 particles. Bob entangled with his, and then send the middleman one to me. I keep it for 2 years. And now I want to send something to Bob. I take that qubit out and entangle it with my qubit. And then I do a measurement. If I get 0, I'm going to call Bob. Because if I get 0, it means Bob has got this state. Okay, I will show you later. And we don't need to show later. Like measuring the BB, because this is 0, right? This is 0. BB is the middle qubit, the middleman one, right? The ancillary one, right? So I get alpha 00 plus beta 101. Then I call Bob, I say I got 0. Then what does it mean? It means my bit is already entangled with Bob's qubit, because when I'm 0, Bob is 0. You can ignore the middle one because now it's useless now, the auxiliary. When my qubit is 1, Bob's is also 1. I only have 0, 0, and 1, 1 state. The reason you have 3 qubits because you have the middleman one, but I can discard it, right? This one, I really can just ignore it. It's just an electron sitting over there. The point is that I am entangled with Bob's qubit. Is this clear? Now, if Alice got 1, then the wave function is going to collapse to 0, 1, 1. When I say Alice got 1, it means the qubit, the middle qubit BB becomes 1, right? So it's going to be 0, 1, 1 and 1, 1, 0. Now, if you look at this, am I entangled with Bob's qubit, by the way, for this one? It's the first right? The MSB and LSB entangle by definition. It is entangled, still entangled, but it is anti-correlated, right? When it is 0, it is 1. When Alice is 1, then Bob is 0, right? Then what can we do? Bob just need to apply a NOT gate to his qubit. And you know that the operation of NOT gate, again, by definition, is what? How it transforms the basis state. When it sees 0, it make it into 0. When you see 1, it make it into 0. When you see 0, it make it into 1. So here again, Bob and Alice qubit are entangled, right? So effectively, by going through this operation, we will have alpha 00 plus beta 11, which is here. We are not cloning anything. I'm trying to find a way to entangle Alice's qubit with Bob's qubit, right? So instead of doing this one through the CNOT gate, now we do this complicated operation to get this entanglement. That is the purpose. And after this is done, then we continue on this operation. So in a full teleportation algorithm, you need 2 cores, 2 classical cores. Okay, and also 1 classical transport for preparation. So it means if I want to transport myself to the Mars, I need 2x of my molecule on Mars. They do all those type of entanglement first, and then they need to send the middle particle to here. Is that okay?
So the difference between this slide and the next is in this one there's no entanglement between Bob and Alice on the student.
The difference between this slide and the next one is that this one is assumed we have a control NOT gate that can span a very huge distance. If we have that, then this can be used for quantum teleportation. But we don't have this. Then how do I successfully do this entanglement? My goal is to create this state, alpha 00 plus beta 11. I need to create this state. I can use CNOT gates, but I don't have such a huge CNOT gate, right? So in order to create this, I need to use this complicated algorithm to create this entanglement. This one is just equal to alpha 00 plus beta 11 if I ignore the BB bit, right? I remove the middle one. This one I get alpha 00 and beta 11, right? Alpha 00 and beta 11 is what I need in order to finish the quantum teleportation. So this whole thing is that to help me to get this only, just to entangle my qubit with Bob's qubit. That's it. I have not done the quantum teleportation. Yes, we're teleporting from Alice to Bob. Right. So, okay, so maybe this is confusing, but I feel this is easier. That's why it got swapped. In principle, you start with this and then continue on this. Okay? But I just tell you a fake version that need the control NOT gates, that if you have a control NOT gate, it's very simple for quantum teleportation. And then I tell you that because we don't have the control NOT gate, we need to use this compressed algorithm in order to do the entanglement. This is to replace the control NOT gate. That is the purpose of this slide. Yeah. Yes. So this is the one Bob start from his lab. He entangled with his qubit. Then this auxiliary bit or ancillary bit will be sent physically to Alex. And Alex keep it until she want to quantum teleport his state to Bob.
So then that's the need for the qubit. The MSB
Yes,
to do that.
yes, because her purpose is to quantum teleport this state to Bob. And we are using this ancillary bit to do that.
The MSB
Yeah, you threw away this BB, but then for the MSB, for an LSB, the Bob and Alice state, they will be in this state. And that is the state ready to do this quantum teleportation. This is the state you need to do quantum teleport. Then Alice will start measuring the plus minus basis and then call Bob again. Yes, yeah. When you get to this stage, you don't need the middle one anymore. Okay, so let's look at some math. This is the more realistic one that we just said. We basically is doing the same thing, but our goal is to do some exercise, right? So that we will be very good in, oh, I lost mine. Anyway, let me see if I can do it. So, okay, and then there's one thing, right? Here I'm going to swap it. I tried deliberately to see if you can see it. Now I make the MSB on top. Okay, because in some paper or textbook, MSB is on top. So this is Alex qubit, right? And then I also have the LSB in the bottom, which is the Bob's qubit. And I start with this BB, the ancillary qubit. Okay, so we all start from 0. Maybe we start from 0 here, 0. And then I want to entangle them. So this is something you need to learn. Well, how do you do entanglement? You will first do a Hadamard gate. And then after Hadamard gate, you will do a control NOT gate. And then Bob and the two qubit will get entangled, right? So if we only look at here, you have 0 BB, 0 B, because I ignore the Alex one because I only look at the bottom. The Alex one has no effect. I can append it, prepend it easily. After control NOT, after the Hadamard gate, what do you get? What does the Hadamard gate do to the BB bit? Very good. Superposition, or you just say become plus state, right? Or whatever. Is this okay? Right? I don't need to go to matrix. Hadamard gates, again, every gate you define it by how it transforms the basis vector. So it transforms 0 to 0 plus 1. And I remove BB and B because I know what I'm working on now, right? And this one equals to what? I want to make it simple. I write it as this. Is that okay? Yeah? 0, 0, 1, 0. And then I do a control NOT gate. What do I get? Again, do it by basis, right? You either use the matrix or think in this way, how it transforms each basis. What would it be? Control NOT. 0 and 1, 1, because for the first one, the controlling qubit, which is the BB, right, is 0. So we don't change anything. The second one, the controlling qubit is 1, so it becomes 1, 1. This is an entanglement state, a Bell state, yeah.
Simple for one here. But plus minus, does plus cause the shift? Minus cause it.
It should be the minus. Okay, so this is the final, this is what we get, and that is exactly what I'm showing here, right? This is the first entanglement. Now then what do I do? So here, this is in Bob's lab. Right? He then sent this qubit to Alex. And now it is in Alex's lab. Okay? You need to physically send it. So Alex has a state which is psi equals to alpha 0 plus beta 1. Make sense? Right? But now in order to study this, they entangle, so I need to really put them together, right? So what is the total state, right? This is step 1, or do I call this? I did not call, oh, this is called step 1A. Still step 1A. What is the total wave function now from here? What is the total state? Zero, zero, zero. No, I mean, it's a tensor product, right? Between Alex and the rest, right? No, I am just asking here. This is before, this is after control not gate already, the first control not gate, right? Yeah, you're a bit ahead. So this one is 0, 0 plus 1, 1. Okay? Which is equals to 1 over square root 2 alpha 0, 0, 0 plus beta 1, 0, 0 plus alpha 0, 1, 1 plus beta 1, 1, 1. How do I get this? Because the psi equals to alpha 0 plus beta 1. Right? So I just do a multiplication. Alpha 0 times 0, 0 becomes alpha 0, 0, 0. Alpha 0, and then beta 1 times 0, 0 becomes beta 1, 1. Alpha 0 times 1, 1 becomes alpha 0, 1, 1. And beta 1 times 1 becomes beta 1, 1, 1. Right? I did not do anything yet. This is just the total state. I saved my writing. I did not write the Alex states, right? But as you just say, you were ahead, right? What happened? Now, if I do a control knot, right? Like here, I use the Alex qubit to do a control knot on the ancillary qubit, right? Maybe just in case you get confused in the future, let me just make the whole box. Okay, and I think it would be useful to you if I write it carefully. If I call this, what should I call it? 1. This is the 1. If I call this 2, this is 2. If I call this 3, 3 should be equal to 2, right? It's just at 3, I added the Alex qubit. And my question is, what will 4 be? So after the control NOT gate, you can either make a big matrix or what is this? Can you tell me based on what I just told you? The control NOT gate only apply to the most significant qubit, the first 2. Okay, it has nothing to do with Bob. Bob has identity gate. What happened to this one? What happened to alpha 0, 0? Stay alpha 0, 0. Because the controlling qubit is 0. Alex is the controlling qubit. How about this one? 1, 1, 0. Because the Alex is 1, so you're going to negate the BB qubit. How about alpha 0, 1, 1? unchanged. Again, controlling qubit, which is the MSB, is 0. And then this one, 1, 0, 1. Yeah. So particularly, you need to live in this domain that you understand the Bob's qubit goes through nothing. It's just an identity gate. So we are not changing anything, right? This controller is only meaning for the 2 most significant qubits. Then you get this, okay? And then eventually it comes to the measurement. Here I won't, I don't have any label on the figure. So Alex will do the measurement. And definitely, she's not going to measure her qubit, right? She's going to measure the BB, right? So if she get BB, if she get 0 for BB, now this time she measure in 0, 1 basis, not the plus minus basis, okay? What is the leftover? This is just the partial measurement concept we have discussed, right? The whole whole system becomes what? If she gets 0 for the BB qubit, for the middle one. Oh, yeah, that's very good. Do we need to renormalize it? We do, correct? Because now we get rid of some basis state, and if you normalize it, I will get rid of 1 over square root 2. Because I already know alpha square plus beta square equals to 1, right? Otherwise, you can just go through the math. Very good. What if Alex get 1? What does the whole system will collapse to what? Alpha 0, 1, 1 plus beta 1, 1, 0, right? Let me remove the bracket. This is just partial measurement. Basically, I could have, we have done in the midterm very long time ago, ask you, you have this superposition state, right? I do a measurement on the middle qubit. What are the possible outcomes? 0 or 1. What is the final state once you do 0? It must collapse to only the one that have the 0 for the middle qubit. That's why it's 0, 0, 0, 1, 0, 1. If you get 1, it must be 0, 1, 1 or 1, 1, 0. Okay? And to make it clear, right, I can discard BB. I don't want BB. Is this a problem? No, because they are not entangled, right? It's just I have 3 electrons. At the beginning, I consider all of them. Now this electron has no use, I just take it away. Or I can reshuffle the order of the electron or put it at the front, right? It can become the MSB. And then I can factor it out, and it is useless again. That's why I can have alpha 0, 0 plus beta 1, 1, or alpha 0, 1 plus beta 1, 0. Is that okay? Now, I apply the identity gate to here. I get this to Bob, right? Alex need to call Bob, say that I got 0, then you don't do anything. Or Bob is going to put the NOT gate to it because Alex got 1. Then Bob is going to get this also, right? The whole purpose is what? Finally, I get alpha 0, 0 plus beta 1, 1. What is the point? Because then we can start from here and finish our quantum teleportation. So you see that quantum teleportation looks like fancy, but if you look into the details, it's nothing so fancy or special. First, you need to prepare an extra electron. You need to prepare for that. So I cannot just say, today I make a friend on LinkedIn, and then I say, let me quantum teleport my information to you. No, then your friend need to prepare some electron and send to you first. And then you go through this process, then you can quantum teleport. So all quantum teleportation requires some preparation. It's not just that I want to do it, I can do it right away. Second is that I need to call my friend using classical channel 2 times in order to make it successful. Yeah, question?
So I guess, it's like a home source and destination.
Only,
To teleport one qubit, you need one X.
Yes.
One qubit.
no, destination, no, it's still one from the destination, but then they need to send it to you. It's still the same qubit, right? This BB, we only need one extra qubit, but at the beginning it was in Bob's lab, and then after he done the entanglement, he will send this to you carefully, and then it's in your lab. So it's only one extra, but this extra is more difficult to having 2 extras separately because you need to transport the electron. Yeah.
I mean, I guess one still is the transfer this ancillary qubit over a channel, assuming you have long enough decoherence.
Exactly. Yes.
State to state.
Yeah. Yeah. Exactly.
Which is, I think,
Photonics is easy to work. Yes. Easier. Yeah. That's right. Yeah.
so the-
Yeah. So these are very important for quantum communication and internet or whatever, which is beyond the scope of the class, also beyond my knowledge. So, but I want you to appreciate that, right? It is important, right? It is important. We can teleport a state we don't know to other place. But all this preparation make it looks like it's not fancy. It's not like violating whatever relativity or all these things. Okay, so everything makes sense, right? You will feel more comfortable after you see this. Yeah, there's nothing super fancy, not really teleporting a mass, but it can be used for some purpose, right? You need to prepare for that. It's just like that. Let's say the Earth suddenly destroyed. Can I teleport myself to Venus right away to save myself? No, you need to prepare for that. Your parents, when you are born, need to start transporting some corresponding molecule to Mars already after they entangle with yours. And you cannot evolve, you cannot grow, you cannot take more molecule. And then you can teleport when you want to leave the Earth. Yeah, so makes sense. Yeah.